All right, so data collection, and the reason I don't care which one goes where, is because I'm just going to see if there's a difference between the thumb and the finger. That's all I want to see, because that's all the parents claimed. I mean, I didn't get the skinny about the one parent who I'm sure said, "Oh, my kid would have won." I have no idea, but the implication is that there is a difference in which appendage is used. So we'll do that. So let me go around the room and let's collect that data up and slap it into L1 and L2. So Rosie, let's go. Your thumb. Let me clear out my list actually. Oh, you didn't have a stopwatch. Who had the first stop? Justine, you didn't have one, right? Dina, you had one? Give me your thumb time first, my friend.
My thumb time was 22.25.
22.25, and your finger time was?
21.56.
21.56. Clearly the finger is faster. Done. End story. Right? Exactly. There's an American view of statistics. Okay, good. Good. Torn, did you have a stopwatch? You did not. Michael, no. Laura, you did?
Yeah.
Thumb time first?
22.01.
0.01, and your finger time?
21.72.
Why are we even doing this experiment? It is clear to me. Thumbs are slower than fingers. Perfectly clear. You didn't have one. You didn't have one, Harrison. Will, did you have one?
Thumb was 21.72.
7.2.
Finger was 21.6.
21.6. This experiment is over. It's done. It's done. This experiment's done. Jack, did you have one?
Thumb was 21.95 and finger was 21.8.
0.8. I don't know why we're collecting data still. They're all showing the same thing, right? They're all showing the exact same thing. I mean, every one of them. Kaylee, did you have one?
I used my thumb and my finger on my phone.
I don't want to include them, not because I'm a bastard, because I mean, there's so many other potentials for control. We can go back and see if it fits later, but let's just, for right now, let's just leave it out. Who's next stopwatch we had that was working? Ryan, you had one? Go ahead, thumb.
21.81 for both.
For both, we're going to throw your data point out because it doesn't support my anecdotal belief. Kidding, of course. Kidding, of course. Next stopwatch. Who had a stopwatch? Oh, Kayla, go ahead.
21.69
Mm-hmm.
and 21.73.
And we're going to throw yours out because it actually refutes it. Kidding, kidding, of course. Please, Chloe.
My thumb was 21.65
Uh-huh.
and my finger was 21.85.
Love it, love it. This is great. This is great. This is great. Ash, did you have one?
Yeah.
You did. Go ahead, thumb.
21.91
91 and?
21.9.
0.9. Excellent, excellent. Dana, did you have one?
Yeah. I had 21.68
6.8?
and 21.43.
4.3? Thank you, thank you. Rach, did you have one? No? John, go ahead.
21.78.
21.78 and?
21.31.
3.1. Thank you, thank you, thank you. Lindsay, did you have one?
My thumb was 21.5 and my finger was 21.9.
21.9? Okay, good. Kayla, did I get yours or no? I got yours. All right, Chris, go ahead, yours?
0.78 and 0.59.
21.78, 21.59. These are pretty congruent with that 21.5 world record time. I mean, ish, somewhere in there.
Okay, 21.59.
21.59, thanks, Kels. And
21.97.
21.97. Thank you, thank you, thank you. 21.97. And last but not least, Josh, go ahead.
21.6
6.
and 21.75.
7.5. Okay, let's make sure we've all got that data. Was everybody able to keep up and get the data entered in? Okay? Solid. Okay, let's erase some of this stuff. I want some of the stuff up here. I want that, I want that. Yeah, still want that actually, because we're going to compare it, looking for a difference. So we'll keep the sign from the last test, just to see if the parent's claim has any merit whatsoever. There's a difference. Because Doug didn't come to me and say that we think the thumb is faster. He just said that we think the thumb is different. So, or the finger is different, whatever it was. Okay, so what should we do as statisticians to test these parents' claims? What should we do to test these parents' claims? What do you think? How can we use our data to either support or refute their claim? What do you think? Ideas? Any ideas?
Build a confidence interval around both.
Mm-hmm.
See if they overlap.
And see if they overlap? Awesome. Build a confidence interval around both and see if they overlap. So let's build a confidence interval around the first. So we do a little T interval. T interval on data, yes. L1, yes. Frequency? Just one. Exactly, because L2 is a different data set at this point. Kind of. We'll come back to that. Okay, 95% confidence interval. The thumb takes between 21.7 seconds and 21.9 seconds. Okay, 21.7. It depends. This also depends on how much precision you want to include. Since we have stopwatches that go down to, I think, 3 decimals, we could probably include more than that. But I got 21.7 to 21.9. That's the thumb, yeah? That's the thumb. With me so far? Good, good. Okay. And let's also do, where's T interval? Here it is. Everything's the same except use the finger now. Same exact setup with the finger, 95% confidence. 21.7, 21.9 was the first one, right? Okay, beautiful. 21.6, 21.8. Conclusion. Conclusion, based on those two intervals?
Fingers better.
There's no difference. No difference. They overlap, correct?
Okay.
Good. Here's a clever thing to think about. What's our confidence in that result? What's our confidence in that result? It's a bit of a trick question. It was on your first out-of-class exam. And then he's looking at me like crazy because we have 95% confidence, right? But we ran 2 intervals at 95% confidence, which means our confidence just went down, didn't it?
93.25.
Yeah, now it's just above 90%. Can you think of a way we could simultaneously test both data sets and maintain 95% confidence? One way we can do it, one way we could do this is by increasing the confidence to 97.5. We could increase the confidence to 97.5. The problem with doing that is, and we're going to get into this more next week, is you increase the chance of a type 2 error by doing that. When you decrease the type 1 error, you increase the type 2. We'll see, again, more of that as you go through the next couple weeks with me. Can you think of a way right now, of testing simultaneously both data sets? And I gave you a little bit of a hint on the board when I wrote down L1, L2, and L3.
You subtract L1 from L2 and then make H naught equal 0.
There, say that again, nice and loud.
Subtract L1 from L2, make that L3 data, and then make your null hypothesis equal 0.
Why would we want to do that? If we subtract L1 and L2 from each other, why would we want to do that? Because then you'd be looking at the difference of them. And if there was a difference, what would the result be? Or if, ask it a different way, if there wasn't a difference, what would the result be on average? Be brave, be brave. If there was no difference between thumb and finger, if there was no difference at all between thumb and finger, what would the average difference be over time? 0. There wouldn't be a difference. It'd be 0, yeah? This is beautiful, yes? This is beautiful. Now we can maintain confidence by creating an interval and or a test around one data set, which is the average difference. That's what we're going to test. Now, see how this is different than everything we've done before? It's different because it looks like we have 2 data sets, doesn't it? Thumb and finger. But it's not. This is actually called something interesting. It's called a matched pair test. A matched pair t-test. Matched pair t-test. These are wicked fun. They're wicked fun because you don't have to have some arbitrary starting value. Think back to every hypothesis test I've made you do so far in this class. Every single one of them had some pseudo-fictitious value that I had to insert into the null hypothesis. Very first one I had to do was testing a flu vaccine. Null hypothesis, I think it was 12%, because 12% usually get the flu in any given year. Next hypothesis test, Florida motorcycle death rate. Null hypothesis, 0.000745. Because gotten from statistical data, the null hypothesis was a percentage I pulled. Next hypothesis test, can you find Iraq? Null hypothesis, 19.7, because that was my geometry problem that I did in the American flag. Next hypothesis test, Prevnar, dropping infant appetites. Null hypothesis, 13.5%. Why? Read it in some journal somewhere. Next hypothesis, see what I'm getting at here, friends? The crowning one was today. Draw 2 dots 3 inches apart. I was reaching. I gotta get something I have a null hypothesis value for. But it's somewhat fictitious, right? It's somewhat fictitious. It requires that you know a parametric value. That you know a value that is a parameter. Anybody else pissed off about that? It's a little bit ridiculous. It's like assuming you know mu. And then you're seeing if mu changed. Well, you have to kind of know mu. The beauty of this is we don't have to know what mu is. All we're trying to see is there is an average time that our thumb takes, and there is an average time that our finger takes, and they're both out there. So there's a mu1 and a mu2, if you will, floating around out there. But rather than assume we know anything about mu1 and mu2, let's look at the average difference between them. Whatever it is, if they're the same, it'll be 0. Does that make sense? So we don't have to know what they are, but if they're equal, it'll be 0. Beautiful. So this is the average difference in your thumb and finger time. So technically speaking, there are two mu's out there. There's mu sub thumb and there's mu sub finger. But we don't have to know what they are. All we have to know is how they compare to each other. That's the beauty of a matched pair t-test. And the null hypothesis is almost always going to be 0. It's almost always going to be 0 because usually you're testing to see if there is a difference or if one's faster than the other. We'll come back to that question momentarily to see if one is actually faster than the other. So yeah, I'm saying we do this and we do this because that tells us, is there a difference? Is there a difference between the thumb and the finger time? Again, burden of proof because, and again, this is directly from the parent's claim. All I heard from Doug that day he was so upset was, there's a difference. Nobody said the finger was faster, the thumb was faster. I'm sure it was a disgruntled parent. But all I know is there's a difference. Go, Kaylee.
Can't you just tell whether or not the thumb or the finger is faster by looking at X bar?
In our sample, for sure.
Okay.
In our sample, absolutely. Our confidence interval, I forget which one it was. I think the finger was faster,
The
yeah?
finger is 21.71 and the thumb is 21.78.
There we go. So it's faster by sample difference of, what is that, 0.07 seconds.
Right.
But again, that's just sample. There's sample error built into that. Will that hold up in repeated studies? I have no idea. What we have to do is make it inferential by taking our sample data, make it standard error, and see what happens. But the thing is, the problem with even looking at it the way you just said is, it's two different studies,
Right.
which lowers our confidence, yeah? Okay, and I don't expect you to believe what I just said about if we raise the confidence, you also increase the chance of a type 2. I don't expect you to believe that right now. Next week, I think you will. But right now, you're like, I don't understand how increasing or decreasing one kind of error can increase the chance of another one. That might not make a whole lot of sense to you. Don't worry, give me time on that. I promise it will. Okay, so here's how we do exactly what Will just told us to do. We're going to go to Stat Edit. Here's your data sets, and they're beautiful. We're going to turn them into one data set. Go on over to L3. Put your blinker up on top of L3. Put your blinker up on top. And then just do L1 minus L2. And then press Enter. There's your differences. There's your differences. Notice, some are positive, some are negative. There's a 0 in there. What do the positive ones mean? The 0.69, the 0.29, the 0.12, the 0.15. What do those mean? That means your thumb was slower because it took the thumb longer to register the stop than the finger. Yes? Everybody buying that? Thumb was slower, difference was positive. The negatives mean the thumb was faster. The 0, that was Jack, right? You were Jack at 21.81, I think. Somebody was exactly the same. 21.81, I forget who it was. Right, you. 21.81, 0 just means there's no difference. But I don't care about individual people. That's why I was joking earlier when I said, we're done the study. One person showed it. I don't care about individuals. I care about the average difference across the entire group again. Yeah? That's the data set. This is actually our data set now. These are the differences in our thumbs and fingers. That's what we're going to test, yeah? Let's do it two ways. Let's do old school and new school. Old school, forget that we're doing hypothesis tests. Let's just run a confidence interval, shall we? Let's just run a confidence interval. Do a t interval. It's set up already for us, but just change your data list to, you got it, L3. That's perfect. That's perfect. Hey, calculate. What do we tell the parents? What do we tell the parents based on our beautiful sample set of size 14? We don't tell them that we might suspect our data set is skewed with outliers. Size 14. unless we're really good statisticians, which we are. Maybe we will. I didn't look at the shape of the data yet. Oops. Sorry. I feel bad now. Hang on. Oh crap! Where are my plots? I turned them off. That's right. Hang on. Arguable, but not terrible. Arguable, but not terrible. Okay. What do we tell the parents, friends? To the parent or parents that said, there's a difference between a thumb and a finger, there's a difference between a thumb and a finger, and therefore we should standardize the way we're timing these races. What do you tell them? Should they be worrying about thumb and finger differences based on this confidence interval? Just focus on that right there. Should they be focused on? Now, of course, the average difference is 0.07, just like Daly said. So there is a difference. Is it significant? And is there a significant difference? I'm seeing some no's, I'm seeing a couple nods, a whole bunch of shakes. Let's try, and then a good pursed lips. Let's try it a different way, shall we? Let's try it a different way. Hold that thought, keep the interval handy. And when I say that, that's kind of a dumb thing to say for a racing rigger. If you would, friends, let's run a t-test as well. Because we have our hypotheses. This is paraphrased as, we believe the parents. This is paraphrased as, we don't believe the parents, essentially. This would mean there is a difference between the thumb and the finger. This would mean there is not. Okay? Let's run a hypothesis test to show us which one we should believe. Yes? So t-test, everything's bomber. Change your null hypothesis to 0, though you do have to change it to 0. Data list is still L3. That's where our data is. You don't want to run L1 and L2. Kids can do the results then. Ready? Here we go. .87 standard deviations. P-value, about 40%. Which hypothesis do we believe? Good, be brave, my friends. We believe the null hypothesis. Why? But when it's big, we believe the null. So, when it's big, why is it big again? Why is it so large? Why is it above 5%? What does a big p-value imply again? Good! The data we got, Danielle, the data we got in the experiment lines up well with what we were expecting in the null hypothesis. We were expecting in the null hypothesis for there not to be any difference in the thumb and finger times. And then we got back our data and the data said, guess what? There's not much of a difference in thumb and finger times. That's what a large p-value means. It means agreement. Which means although the parents want you to believe there's a difference, and maybe they even quote the 0.07. Maybe they do. But you come back and say, yes, it's 0.07, but the 0.07 is not statistically significant. At which point they ask you to stop coming to swim meets. Maybe. Right? Is that fair?
And taping their kids.
And taping their, well, they definitely asked me to not do that. But you see, this is a measurable way of disproving a claim. Or, I shouldn't say you're not disproving, you're not supporting a claim, if that makes sense. You're not proving or disproving anything. You're just saying there's no reason to believe that claim. Now, if our sample size was much larger, i.e., if we got the exact same data, but the 0.07 difference, but we saw it over 2,000 trials, then it would be statistically significantly different because the margin of error would shrink down so far. Did you catch how the confidence interval, this is why I told you not to get rid of it. The confidence interval is asymmetric. There's less negative than positive. This means within this interval, there's more evidence of the thumb being slower than the finger being slower because there's more positive numbers than negative numbers. That's a crappy way of thinking about it, but that's literally what's going on mathematically. Well, if you can shrink that margin of error down, eventually if you can come up 0.11 this way, and then 0.11 down this way, eventually 0 won't be in there anymore, will it? It'll remove itself from 0, and then you can go, oh wait, thumbs are slower. But what is the big assumption you're making by doing that? And this is what I broke to Kimberly when she said 0.07. What are you assuming if you replicate this study 1,000 more times? What assumption, what big assumption am I making right there? That what's going to stay the same? Yeah, well, the p-value will change. It'll get much smaller. I guarantee that. I guarantee that over 2,000 trials. But what will most likely change also? What number did Kaylee quote earlier? When you said, look at the thumb and the finger times, they're different by 0.07. Do we have any indication that says it's going to stay at 0.07 if I run the trial again? No, it's most likely going to change too. It might go negative. It might go positive. I've never gotten a result in this class with this experiment that shows anything like besides what you guys just saw. Every year, every term, I go back to Doug and say, you can tell your parents again. He's like, dude, my kids graduated like 5 years ago. But go back and tell the swim club. Nothing to worry about. He's like, dude, they use touchscreens now. It's 2013. It's all good. It's all good. It's still a perfect place for this kind of thing. Yeah? So Jack, next time you're picking tires for your downhill bike, if you can do this in an equalized fashion, try 2 different pairs out. Run a bunch of trials. Great way to do 10 trials on a mountain bike course. Do 5 and 5. Check your time differences. See if there's any differences, yeah? Perfect way to test them out. Perfect way to test them out. All right, let's do this. Let's talk real quick. Can you bring questions on Tuesday? I think we have an in-class exam scheduled for Thursday, I think, right? For Thursday. It'll be over whatever the last 3 homeworks were, which were Introduction to Hypothesis Testing, 1 Prop Z testing, and let's bring questions on T testing for Tuesday as well, to make sure we really get the idea of this. This has all been T testing. In other words, hypothesis testing on a single set of data around an average. Z testing was hypothesis testing on a single set of data around a proportion. That was your quiz you just turned in. I posted a quiz for Thursday of next week on T testing. I'm going to put at least 1 more up, maybe 2 more up on matched pair testing. There was 1 more data set I wanted to play with today in class, ran out of time. And it's on the back side. You guys ever noticed commercials are louder than your TV shows when you're watching TV?
Yeah.
Okay, we're going to test that. I got some data for you to test that with. Because Congress, if you remember, when they used to work, they tried to pass a bill. They tried to pass a bill that would outlaw that, would outlaw jacking commercials, audio levels. And a researcher in Texas actually did. I've lost the source, unfortunately. You have the data in your data sheet. What I'll do is I'll copy and paste it into a quiz for you guys, and we'll put a quiz up for you guys for next week. You'll test to see if there's any increase in volume between commercials and shows.
If there was, why would they be, what's the point?
What's the point of what?
What would be the point of doing that if they're
advertising
assuming they're
What's the point of doing what?
raising the volume?
If there is.
Well, I've heard all kinds of reasons because that's when you get up and walk away from the television to like get food, that way you still hear it, get your attention. Just because we're Americans, you have to be yelled at, kind of thing. There's all kinds of, I've heard all kinds of reasons as to why. We'll test it. We'll see if it holds up. Cool. Oh, because your frequency is actually is just 1. 1. There you go. There it goes. You got it, Justine.
So simple.
Yeah, I mean, whenever you have raw data, your frequency is always 1. Thank you, guys.